Tulsi madam, please begin.
We have to start the recording, I think, sir.
Madam, Google has stopped that feature.
Okay,
That
fine.
it is will be live on the Facebook only,
Okay,
and it will
okay.
be recorded on Facebook only.
Okay, sir. Thank you. Good morning, everyone, for accepting the invitation. Am I audible, everyone? Hello.
Good morning.
Yeah, good morning, ma'am. So I am pleased to inform you all today we are here with Dr. Bhumika Choksi, ma'am. Also, I would like to say thank you for accepting the invitation. And before hand over to Dr. Bhumika, ma'am, I would like to share a brief introduction. Ma'am completed her PhD from SVNIT Surat in 2018. Ma'am has published many research papers in Scopus Index and ASCI. Her area of interest is fluid flow through porous media. She received a PhD fellowship as a JRF and SRF in different years. She is a life member of Gwalior Academy of Mathematical Science and Gujarat Ganit Mandal. And today's topic of webinar is a mathematical modeling of a real life application. And I would like to hand over the session to you, ma'am. You can start now, ma'am.
Good morning. Good morning to all. First of all, I would like to thank to the organizing committee and Parul University and Professor Tulsi Sheth ma'am for inviting me to give my views on my research work. So today I'm going to take one application of oil recovery problem. So my topic is mathematical modeling of a real life application. So I'm going to focus more on mathematical application. So first of all, I will start with these outlines. So I will introduce what is the oil recovery problem and the necessity things to model one of the fingering phenomenon very much important in oil recovery problem. So these are my outline, and I will start with the introduction of oil recovery problem. So nowadays, you have this idea that every day the prices of oil, that is crude oil, like petrol, diesel, and CNG gases are increasing. And this time it is at the top. And this are not renewable sources. So what can be done to get maximum benefit? So how can we recover the maximum crude oil, whatever we have in the oil reservoir? So this is the basic major issues nowadays for each and every country. So that's why I chose this topic because it has a very wide applications, and we can start with this oil recovery problem. So I prefer that this should not be the one-way interaction only. It should be two-way communication. You can ask your queries in between also, and whenever you have any doubts. I hope we have studied this. What is oil recovery? So there are basically three types of oil recovery process: primary, secondary, and enhanced or territory. You can see the diagram on the slide such as figure number 1. And what are the basic difference between these three process? So primary oil recovery means what? So when we can recover oil by natural pressure only. You can see this in figure number 2. And by natural pressure we can extract only 20% of the oil from the oil reservoir. So that is very less. So for the remaining oil, we have to go for the secondary oil recovery process. And what we have to do in that, so we can inject different things like water or natural gas or carbon dioxide or anything, any other gases to extract the remaining oil. And by this injection process, we can, after that also, we can get only 25 to 35% oil of the remaining oil. And after that, the last process is enhanced oil recovery process or tertiary oil recovery process. uh, in that, you have to what we can do in that process. So in that process, there are many more nowadays innovations are there, but basically three major categories are there, that is chemical, thermal, and miscible. In that other processes, you can say microbial injection, electrical, leaching, or mechanical injection type of process. So by this enhanced oil recovery process, we can get again only 30 to 60% oil from the oil reservoir. So this is the highest limit. Still, there are more research and innovations are there to extract maximum percentage of the oil from the oil reservoir. So uh, when we want to extract oil after natural pressure, so when you want to go for the secondary oil recovery process, so in all this processes, the best and most used and the cheapest process is water injection. So it is worldwide used process, mostly used process. So in that water injection, what is happening in the oil reservoir? So that is called displacement processes through porous media. I will explain what is porous media, what is fluid flow through porous media. But let me just explain first of all my problem. So you can see the schematic diagram of water injection in an oil reservoir. This is a oil reservoir. In that you can see the green color is shows the oil, and this blue color is the water injection. So from left hand side, by the injection well, we are injecting water in the water reservoir, and this water will displace the oil. It will increase the pressure in the reservoir oil, and it will oil will go to the production well, and from that production well, the 25 to 35% maximum oil can be recovered or can be abstracted. So you can see this schematic diagram, and these are the macro version uh, for the different portions. So this is water injection process, and I'm going to focus one of the phenomenon during water injection only. So what is happening inside actually? If I'll go more deep, then this is the process actually uh, occurring inside. So when we are injecting water, so water will come across or will be in the contact of oil, and because of the difference of viscosity and the mobility ratio, there will be some instability or disturbance will occur. So what will happen at that time? So water will try to, let me show you one more figure like this. Suppose I'm injecting, this is schematic representation. Suppose I'm injecting water from the left hand side in the oil reservoir. This is full oil reservoir. So water will try to enter into the oil region, and in the counter effect, oil will try to enter in the water region. So left hand side is water region, and this is your oil region, native oil region. So you can see the shape will be like fingers. So this disturbance or instability, so will be like you can say the word is counter current imbibition, and this finger shape is called another phenomenon, the word is fingering phenomenon. This is the figure you can see, actual figure. You can see in on the slide. So first imbibition phenomenon is occurring, and then fingering phenomenon is occurring. So all and all both together is called fingero-imbibition phenomenon. Okay, so this is our problem that here what I want to do, our main goal is what? How can we extract maximum oil from the production oil? So this oil quantity I want to get maximum. So what we are doing by injecting water, so if I'm getting maximum saturation of water, then that means maximum water is going into the oil region. So this oil will be displaced maximum towards the production well. So that's why ensure your ratio of the oil will be increased. So this is our main goal, and for that I will explain the mathematical modeling and mathematical equations, governing equations. And for this I need some basic criteria of fluid flow through porous medium. So for that, I'm quickly going to this part. What is fluid? So I hope you know what is fluid. So can I get an answer from the audience? Examples of fluid or fluid flow. And I'm going to explain what is porous media. No? Okay.
Any liquid, we can say any liquid type which can if we put in on the surface and it flow, then
Okay.
it's called a fluid.
Yes, very good. So, in short, you can say anything which deforms continuously. Anything. So it can be liquid, it can be gas, it can be plasma. And this act of deformation, continuous deformation, we are calling it flow. Okay, so that is called fluid flow. So any fluid can flow. So fluid flow through porous medium. So what is porous media? So anyone can answer? What is porous media? Porous medium, any example? The word itself says the meaning pores, porous. Okay, so it is the combination of pores and medium, porous medium. So you can see the figure, any material which has pores or void spaces, for example, sponge or braid or cement or wood or rock or our bonds, anything which has void spaces, void regions. So it is called porous material. So in this porous material, I need these two words. So I'm not going to explain everything authentically. I'm just giving you the main concept. So I'm not reading the authentic definition. I'm explaining you the concept. Okay, so you can find all these definitions online and in my research papers also, but I'm just giving you the main concept. Okay, so porous medium which contains pores or voids, and in that, in this whatever the portion, the word is skeletal portion, you can see we are calling it as matrix of ring, and the raised pores are most probably filled with fluid. So most probably fluid, it can be gas. You can see in braid it is gas. Okay, so it is not necessary. It should be liquid only. So this is called porous medium, and fluid flow through porous medium. So our oil recovery problem, you can imagine, it is a part of this major subject, fluid flow through porous medium. So under the ground, under the oil reservoir, this is the fluid flow through porous medium phenomenon. And especially I'm going to focus on fingering phenomenon. And in that, I need heterogeneous porous medium. So for that, I need this two basic definitions. So what is the meaning of porosity for porous medium? So it is nothing but the property, or you can say ratio of volume of the void spaces to the total volume of the porous medium. So it will be always in between 0 and 1, or you can say 0 to 100%. So this is denoting by, we are denoting it by phi. And permeability. So by the word itself, it indicates the ability of the fluid to flow through medium. So permeability, that means ability to flow of any fluid. Okay. And this equation number 2 is given by Darcy's law. I will explain how it came. So it is given by V is velocity of the fluid, K is the permeability, and mu is the viscosity, P is for pressure, and X is for thickness of the porous medium. I will explain how this equation number 2, Darcy's law, came. And based on these properties, there are basically two types of porous medium. There are other porous mediums also, but I'm not going into that part. I'm focusing on these two types of porous medium, homogeneous and heterogeneous. What is the difference between homogeneous and heterogeneous? The word itself says homogeneous means whatever the parameters, certainly we are focusing on density, pressure, permeability, porosity, whatever the parameters are there, they are uniform or same in specific region of the domain. So that is called homogeneous porous medium. So permeability are same, porosity can be same, density. So whatever the region or sub portion you will choose from the porous medium, you will get the same values. So the word we are using homogeneous porous medium, and other, if it is not like that, the word we are using heterogeneous porous medium. And in our real life problem, in our real world problem, oil recovery problem is based on heterogeneous porous medium only. So this is the ideal case. So homogeneous is the ideal phenomenon. And yes, I have paper on both the porous medium. You can see in my Google Scholar link, and I will share the papers at the end of the slides also. Okay, so all in one, fluid flow through porous medium is what? So fluid is passing through porous medium, and in that you can see now that there can be many possibilities for the fluid. So it can be single phase fluid, it can be multiple phase fluid. And what is the meaning of single phase fluid? That means from the porous medium only single fluid is passing. For example, if in our reservoir only oil will be there, we are not injecting anything, no other fluid, no other liquid, then this problem will be from single phase fluid flow system. Okay, and if we are injecting for the secondary oil process water, and for the third or enhanced oil recovery process we are suppose injecting chemicals, some chemicals, so it will be multi-phase flow problem. Okay, so today I'm going to discuss about water injection, so it will be double phase flow problem. Phase we are denoting liquids. Okay, and specially immiscible liquids, miscible fluids, or Miscible liquids means fluids which can be mixed with each other. And immiscible means if they have different viscosity and different capillary pressure. We'll explain what is capillary pressure also. So this is the basic to flow through porous media, and I need this also for my mathematical modeling. So reservoir fluid properties. So what are they? It is the meaning of phase. I have already explained. Phase means different fluids we are denoting as phase, different phase. So oil, water and gas, and we are denoting it by suffix or subscript O, W and G. So in our modeling, O for oil, W for water and G for gas will be there. So what is the meaning of saturation? Saturation of anything. It can be water, oil or gas. So we are focusing on water and oil. So it is nothing but the fraction of the pore space that occupies the phase. It can be water, oil or gas. Saturation of water we want to find in our problem. Then for two-phase flow, that means for water injection, it will be water and oil. So saturation of water can be denoted by SW and oil can be denoted by SO. So by the property itself, saturation, we are calling that our porous medium or our region is fully saturated. That means whatever the phases will be there, the total answer of the saturation will be always 1. So in the same way, if we have three-phase flow problem, that means saturation of water, oil and gas will be 1. So total will be 1 always. So that's why the word is fully saturated porous medium. Okay, and this is capillary pressure. What is the meaning of capillary pressure? Denoting by PC. That means difference between the pressure within the non-wetting phase and wetting phase. So what is the meaning of non-wetting and wetting phase? That is authentic definition, but for your understanding, I'm just explaining non-wetting phase. So the phase or fluids with higher viscosity. For example, we are taking oil. It's not wetting the region, and wetting phase we are considering here as water. So difference between these two phases pressure is called capillary pressure, and always pressure of oil is higher than water in our problem. So PC is denoting by PO minus PW, pressure of oil minus pressure of water. Now, I hope there is not any query till yet. Is there any query? So I will explain what is Darcy's law, and I'm going to use this main governing law for the modeling. So what is Darcy's law? Again, I'm just explaining the concept. So in middle of the 19th century, Henry Darcy has introduced this Darcy's law. And to derive this Darcy's law, what he did, he took a tank of 3.5-meter height. This is one cylinder or tank, you can say, of 3.50-meter height with circular cross section, and it has filled it with lower part is filled with some porous material. Can assume like sand. So of 1 meter height, and then water is added into this apparatus, so into this tank. So from this model inlet, water is added, and from this outlet, water is coming out from the bottom of the tank. So in between, porous medium is there. So this is our problem of fluid flow through porous medium. So which rule is applied here. So by using our regular governing laws, Darcy has investigated that the water discharge, capital Q, is directly proportional to the cross-sectional area. This is our apparatus, and this is the cross-sectional area, capital A. So it is discharge is directly proportional to the cross-sectional area, capital A, and the pressure difference, this is head drop difference, means pressure difference H2 minus H1. So at top, pressure difference, head difference at top and bottom, we are taking H2 and H1. So it is directly proportional to the pressure difference and inversely proportional to the flow length through the porous material. So whatever the difference of the length, flow length, we are considering it as L or delta L, you can say. So by combining this, is there any query from the audience?
No, ma'am. Everything you explained is good. So you can go ahead. It is understood, ma'am.
Okay, I think Neharani Wadhwa ma'am has some query. Yes, ma'am. Yes, am I audible, Wadhwa ma'am? No? Okay, she is unmuted. Okay, so whatever the discharge will be there, if I'll combine all this together, so by taking the constant K, so proportionality constant K, so it will give you the hydraulic conductivity. Ma'am, Vadhva ma'am has some issue, I think. Can you mute her?
Yeah, ma'am. I'm calling her.
Okay. Okay, thank you. So K, we are taking proportionality constant K as hydraulic conductivity, and all three can be written together by equation number 7. So this is our main governing equation. And if I want to find flux, so if I'll divide this equation by K, cross sectional area A, so I will get small q is equal to minus K into pressure difference divided by mu. So mu is our viscosity and delta P is a pressure difference, pressure gradient. So this is our equation number 8, another form of Darcy's law. So this is the basic criteria I will need in fingering phenomenon, and here I am going to explain it in heterogeneous porous medium. So let me start the mathematical modeling of fingering phenomenon. So I have already explained what is fingering phenomenon. It is nothing but the displacement, one of the displacement process, or you can say instability process, which is in the shape of fingering. And for the mathematical modeling of this, I hope everyone knows about mathematical modeling. What is the meaning of mathematical modeling? Can anyone like to answer? Or else I'll explain it in deep. No, mathematical modeling is nothing but the uh, mathematical formation or mathematical equations by the using of governing laws and including all the parameters of our real life problem. So whatever equation we are getting at the end, that is called mathematical model. So here your mathematical modeling will give you a highly nonlinear partial differential equation, And here I have solution by homotopy perturbation, Sumudu transform method. There are so many other methods also. I will discuss it later on. So fingering phenomenon, for that, this is our statement. So here what we are doing, this is a schematic diagram. So this is our oil reservoir, and from the left hand side we are injecting water, and this is native oil O. So this finger shape will be there. Water will try to enter into the oil region, and in the counter effect, oil will try to enter into the water region. But our main goal is to find this maximum saturation of water. So for that, what we are doing, we are taking the average cross-sectional area, and these fingers are irregular in shape. So we are making it into a regular shape. So again, this is not perfectly defined, and we can't find the perfect value of these fingers, rectangular fingers. So what we are doing at the end, we are taking average cross-sectional area of it again. Let me explain. So I will consider the average value. So our main goal is to find this value, saturation of water value. So if your saturation of water is higher, so you can see this wet water is entered. That means we can say water is entered into the oil region, more oil region. So more oil can be recovered from the production well. So the simple criteria we are using in modeling our mathematical equation. So for that, Shediger and Johnson gave this relationship between the permeability and saturation. So, permeability of water and saturation of water is the same. And if we have here, you can see here on we have only two-phase system. So oil and water, only two phase we have. So it is fully saturated system. So that's why I can write saturation of water plus oil equal to 1. So again, permeability of KO is equal to SO is equal to 1 minus SW. So given by equation point 1. And this is the Darcy's law for velocity of water and oil. The same rule given by equation number point 2 and point 3, where we have considered heterogeneous porous medium. So the properties are not same, not homogeneous or throughout the region. So that's why K is the variable, permeability is the variable. So it is not our regular constant, but it is Kx. Then equation of continuity, we know equation of continuity in flow is same as outflow. So by that you will get this equation number 4 and 5 for water and oil. And again here phi is for porosity, and it is again for heterogeneous porous medium, a variable. So that's why this phi is also, as we are considering phi of x. And yes, I have taken here, we have taken only uh, variable in x direction. So through distance part only, but yes, there are new research. You can see the variables quantity, this k and phi will be, you can find the papers on two direction, x and t also. So it will introduce more complexity in the problem. So two-phase problem, again fully saturated. So both the saturation will give you the value 1. And then capillary pressure. So capillary pressure is directly proportional to the saturation. So it is minus beta sub SW, and This is, we know, difference between oil pressure and water pressure, given by equation number 7. And if I'll simplify this, if I'll remove water pressure from all these equations, I will get equation number 10.10. And initial conditions we are considering for initial point at x is equal to 0. Okay, so x is equal to 0 we are considering. Let me show you in figure. This we are taking as x is equal to 0 initial stage. So when the imbibition surface will be there, this point, this boundary, at this point, imbibition is occurring first of all, and then fingering phenomenon. So this x is equal to 0, this is called imbibition surface also. So for x is equal to 0, we are considering condition SW0, and for time 0, we are considering it as SWC, it's constant, exponential constant. So we are considering e raised to x by L by the reference by Verma sir. Okay. Now, this will be more complex, more parameter is there, and dimensions are also not unique. So what we are doing, we are converting equation number 10 into dimensionless variables by considering capital X and capital T, and we will get equation number 11. And this is our, you can see this is our non-linear partial differential equation, and here phi is also a variable, SW our main goal, our main variable. So this will be you can say highly non-linear partial differential equation, and this equation cannot be solved by our regular ordinary analytic methods, so like finite element method or finite difference method or finite volume method. So we will need more advanced method to solve this highly nonlinear partial differential equation. So just I'm simplifying this, I'm separating the terms, and constant terms I'm assuming as capital A and capital B. So this is the main goal to solve. And our main parameter, main variable is to find saturation of water. And for this, I have used homotopy perturbation Sumudu transform method. So I am not going deep into the method because again it will take one more session. I'm just highly giving you the concept. So in that we are introducing Sumudu transform. It is one kind of linear transformation. Whatever you have learned in Laplace transformation, Laplace transformation has their own limits, and here the parameter u is introduced, so we can use these values throughout the negative and minus tau 1 to tau 2. This is the advantage to use Sumudu transformation, and it is given by equation number 13. And this Sumudu transformation I will apply on this equation, and I will replace SW by S for more simplification. And then you will get Sumudu transformation. For example, this is a symbol of Sumudu transformation I am taking of saturation of water. And after that, what we will do, like our Laplace transform problems, whatever we are doing to solve this, so that same procedure I will do. We will apply next inverse Sumudu transform on the answer, whatever we are getting here after simplification. And after that, to get or to remove the non-linearity, I have to introduce homotopy perturbation method. What is homotopy perturbation method? So it includes the homotopy parameter, and it is called P, and again a big one more than one session topic. So it it is Potter parameter. What we are doing for this solution, we are considering a series with Potter parameter like summation p raised to n into s raised to n, and this will be including the His polynomial, so given by His and given by equation number 15. So you can see the form of His polynomial, and what we are doing, we are just simplifying everything. We are comparing the powers of p on both sides and adding all of them. I will get this solution. So I have just counted only first few terms, so till t cube. So you can go beyond it. So I have approximation till t raised to 7. Okay, but here I have introduced only t cube power term. So this will give you the saturation of water. And yes, we have considering only, we are considering only few terms. So this will be the approximate solution for saturation of injected water. And this is our final solution after homotopy perturbation method. And from this, what we are doing, I'm taking different values of x and t, and because it is dimensionless, we have already converted it into dimensionless parameters, so I can choose values of x and t in between 0 and 1. So for graphical and numerical representation, so I have choose x is from 0.1 to 1 and t is from 0.1 to 1. So I will get this saturation of water, injected water, for different x and different t. And you can see by for particular time, if distance is increasing, you can see the saturation of water is increasing. Okay, so if I'll show you the graph, different graphs, saturation of injected water versus x for fixed t. So I have fixed the t like 0.1 to 1. You can see the saturation of water is increasing as distance is increasing. In the same way, with time also they are increasing. So this is our main goal, that if saturation of water, injected water is increasing, that means the more oil is traveling towards the production well, and implies we can cover more oil from the production well. So this is our conclusion. So by homotopy perturbation method, we can extract maximum oil by increasing saturation of injected water. And these are the references I have used here. These are some publications, some of the publications, major publications I have introduced, and the research papers I have presented in seminars and conferences. So thank you all once again, and if you have any queries, you can ask. Is there any queries from the audience?
I don't think so, ma'am. You explained each and everything. You explained each and every definition, and very good diagrams and presentation you gave here. So I think no one has any query. And thank you, ma'am, for the informative talk and the session. We can close, I think, now. View webinar.
Thank you all. Thank you so much for inviting me. And yes, whoever has queries, they can contact me on my email ID. I have already shared it in the slide. And you can see my other research papers also. You can reach to me with this mail ID.
This audience can note down the mail ID if they want to go in detail, or if they need any information, then they can contact ma'am on the mail ID.
Thank you. So,
Thank you, ma'am. We can end up the call now.
thank you. I'm leaving.